Hey, welcome to the Flipped Classroom and your first video for the year. We are studying unit number 1, which is talking all about matter, chemical trends, and chemical bonding. And today's video is going to give you some background information on how to calculate the average atomic mass for an element, given some data. I invite you to take notes. I invite you to pause, rewind as needed. And most of all, if you have any questions still from this video, put them on a sticky note on your notes that you're taking. Bring it into class tomorrow, and we'll be sure to answer it. To introduce you to the notion of average atomic mass, I'd like to actually begin with an example of something that applies to you. I want you to imagine it's the end of the semester and you're me, and you've got to calculate a final mark for you. And note that your final marks are calculated on weighted averages from a number of your summative assessments, but they're also based on a certain number of categories. So in science, all of your weightings are 25% for knowledge and understanding, for thinking and inquiry, for application and communication. In other courses, you could have different weightings, which you can see here. And those weightings are outlined and given to you by your teacher at the beginning of the year. And if you're not sure what they are, by all means, always feel free to ask. So what I'd like to do is let's assume that you get a certain percentage on all the marks of your summative assessments in these categories. And let's compare and contrast how weighted averages could affect the outcome of your final mark. So like most students, let's assume that your knowledge and understanding base, is say, 80%. And you get a mark of 80 in your term mark for knowledge understanding. And maybe thinking and inquiry is a little tougher for you, so you get a 75. Application sometimes being the toughest, let's say you get a 70. And in communication, you take your time, you make sure that you're using correct units and spelling and so on, and you're good at communicating, you get an 85. And let's keep those same grades over here for course number 2. And course number 2 has, as I said, different percent weightings for each of those categories. Now, if we go through and we do a little bit of multiplication here, we can take 80 times 25%. Now, when you punch this into your calculator, you can either punch in your 2 button, your 5 button, and your percent button, or you can convert that percentage to a decimal instead. And so in order to make it from a percentage to a decimal, percent means divide by 100. So 25 divided by 100 means the equivalent decimal to 25% is 0.25. So if we go to your calculator and we punch in 80 times 0.25, we find that the value comes out to being 20. In a similar fashion, if we take 75 and multiply it by 25% or 0.25, we get 18.75. If we take 70 and multiply it by 25%, we get 17.5. And lastly, 85 times 25% or 0.25 comes out to 21.25. And as all of these percentages would add up to 100, we can add up all of these to see what your overall term mark would be. And when you add them up, it comes out to 77.5, which as a good teacher, I would round that up to 78%. I'd never leave you at 77.5 or round you down. I would always round you up. Now, in a different course, let's look at those same grades and see what your term mark would be. So 80 times 20% or 0.20 would come out to 16 marks that would count towards your term mark. In the next line, we would have 18.75 if we multiplied 75 times 25%. 70 times 40% or 0.40, taking that decimal place over twice, would give us 28. And 85 times 15% would be 12.75. So again, in the same way that all of these add up to 100, we could add all of these up to get your total mark for the term. And it comes out to 75.5, or again, it would be rounded up to 76. So isn't it interesting that your term mark would be different depending on how the different components of KU, TI, A, and C are weighted for that course? Now let's take this one step further. Let's also add in here your exam mark. So let's assume on your exam, maybe you get 75% in the KU section, maybe you blow a couple multiple choice, you get 70 in the thinking inquiry and 70 in the application, and maybe 80 in communication. And let's look at our course versus course B over here. Let's say you got those same percentages, but again, the exam weightings for this course are a little different. They match the weightings of the term for that course, but let's see what you would end up with a mark of on the exam. So over here we would have 18.75, and again, know where these numbers are coming from. Try punching them into your calculator to make sure you can get them. And as this adds up to 100, so will this to be your term mark, which comes out to an exam mark of 78% overall. And then over here, if we do a similar thing, we can see that 15 of your marks from the exam would come from the KU section, 17.5 of your percentage points on the exam would come from TI, 28 would come from here, 12 would come from here. And again, if we add them all up to get your final exam mark, you'd end up with a 73% on the exam in this course. So this student in the first course right here has 78 terms, 78 exam. If you had the exact same marks, same categories, this student would have 76 on term and 73 in exam. So the next question becomes, how does that affect you overall? Well, now you're told that your term mark is worth 70% of your final mark and your exam work is worth 30. So this is what teachers do. In course A, which would be a science course, for example, because we're all weighted 25, 25, 25, 25, your final mark would be this. Your final mark would be a mark of 78 term, which is worth 70% of your final mark, and a mark of 78 on the exam, which is worth 30% of your final mark. And so that comes out to 54.6 plus 23.4, and you end up with an overall mark of 78, not surprising. 78 going in, 78 exams, going to give you 78 overall. In the other course, the final mark would be equal to your term mark of 76, which is worth 70% of your mark overall, and then a 73 on the exam, and the exam's worth 30% of your overall mark. And so this student ends up with an overall mark of 75% as a final grade. So therefore, you can see that the weightings of each of those categories have an effect on the final value, or in this case, on your final grade in a particular course. So how can we apply this to average atomic mass? Well, isotopes are the things that we're looking for instead of marks, and the percentages have to be given to you to know how abundant they are in everyday life or out in the natural world. So what I'm going to do is I'm going to take you through a boron example, and I'm going to do a little bit of Bohr-Rutherford with you and then do a similar calculation as before. So if you are told outright that 19.9% of all boron atoms in the world are boron 10, and if you are told that 80.1% are boron 11, and remember you have to be given those percentages, I don't expect you to know them, but you could Google them too. If they're boron 11, then the question becomes, what is sort of the overall average mass of boron atoms, because they're not 50-50. They're not all 10s, they're not all 11s. They're obviously a little different. So let's go back again and just review quickly what an isotope is by looking at it from a Bohr-Rutherford standpoint. We know from this notation that the bottom number, of course, is the atomic number, which means that there are 5 protons in a boron atom. And every atom in the world that has 5 protons is defined as boron. And we also know that if there are 5 protons, there must be 5 electrons. So we can put 2 in the first shell and 3 in the second energy level there, and 2 and 3. So far, these 2 atoms of boron look perfectly identical. Same protons, same electrons. However, what makes them different and what makes them classified as isotopes is the fact that their neutrons are different. How do we find the neutrons? Well, we know that this top number is protons and neutrons, and we know that this bottom one down here is just protons. So if we take the sum of both of these and we subtract off or peel off the protons, we're going to be left with the number of neutrons. So in this case, 10 minus 5 means that boron 10 atoms have 5 neutrons, whereas boron-11 atoms have 6 neutrons, and that's what makes them critically different. So how do we find the average atomic mass for this? Well, we're going to do it in a similar way that we did to finding our mark overall. The average atomic mass for all boron atoms in the world is equal to the boron 10 atoms, which have a relative percentage of 19.9, or we can change that to a decimal as being 0.199. Just take the percentage here and divide it by 100 to get the right decimal. And we're going to add into that our boron 11 atoms with their relative percentage, and their relative percentage is 80.1%, or 0.801. And if we add each of those little pieces together, we find out that overall, the average atomic mass of boron is in fact 10.80. And we write a little U here to talk about atomic mass units. We'll get it to changing that to a different unit a little bit later in the course. But for now, if you see that U in textbooks, that's all it means. This is not surprising to us that this final answer down here is closer to 11 than it is to 10, because look, more atoms are of the boron 11 type than of the boron 10 type. So, you know, we're going to shift a little bit more towards 11 than we are to 10 because there's more of these. And so the average atomic mass is somewhere in between. It's not 50-50, it's not 10.5, it's closer to 11. Let's look at one more example just to clarify this. Let's use chlorine. So for chlorine, if you are told that 75.77% are of the chlorine 35 type and 24.23 are of the chlorine 37 type, the question becomes, what is the average atomic mass for chlorine? Well, all we need to do, and we don't even need to do the Bohr-Rutherford structure to calculate this, but again, I will reiterate just from an atomic standpoint what makes an isotope an isotope. If we look up chlorine on the periodic table, we find it is element 17. Always, 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 always. Of course, that atomic number means that there are 17 protons in here, and there would be 17 electrons. Following Bohr-Rutherford's rules, got 3 left, 1, 2, 3 to get to 17 electrons. And of course, on this side, we would have the exact same thing. Isotopes have the same number of protons, but differing numbers of neutrons. There we go. How do we figure out the number of neutrons? Well, remember that the mass number minus the atomic number tells us how many neutrons there are. So 37 minus 17 would have 20 neutrons over here, and this one has 18. Okay, now let's predict a little bit ahead of time. What is the average atomic mass value going to be like? Well, we can see that the chlorine 35 type, you know, are more predominant. Almost 3/4 of them are chlorine 35s, whereas only about 1/4 of them are chlorine 37. So we're going to anticipate that our final answer is going to be closer to 35 than it is to 37. Let's check. So of all the chlorine atoms in the world, there are 75.77% that are of the chlorine 35 type. And there are 0.2423% of all chlorine atoms in the world of the 37 type. And if you punch that into your calculator, you will find that the average atomic mass with the data that you were given is in fact closer to 35. It comes out to 35.48, which is very close to the value on the periodic table of 35.45. There are some rounding errors that contribute to that last decimal being off just a little tiny bit, but it's pretty darn close. So to summarize, average atomic mass is based on the percentage abundance of an isotope, or of all the isotopes of a particular element. And the most predominant one is going to have more of an impact than the isotope that is not so predominant or not found so often. And this is a typical type of question that you can see on a test and so on, and I encourage you to practice it and try it. If you have any questions, don't hesitate to ask me.